Well, there are several ways to do that, and these ways can be split into parametric approach and non-parametric approach. If we know which distribution a statistic follows, and if sample is good enough, so we don't have severe outliers or any other problems, then we can use a parametric approach, which is a simpler. This is what we have learned last time, right? But if sample is not good, or if we don't know which distribution statistic follows, then we need to use a special methods which are called non-parametric statistics. And we are going to learn non-parametric statistics at the last block, at the block number 4. So here we will learn how to use parametric statistics to make an interval estimate for population parameter, to find the confidence intervals. So what it means? It means we will follow the same sort of algorithm as we did before. First of all, we need to find out which distribution to use. So we need to know which theoretical distribution your statistic follows. So it means that if you take 1,000 samples, how the statistic and calculate statistics for every sample, so you will end up with 1,000 values, for example, 1,000 average values, how they will be distributed, what the theoretical distribution they will follow, okay? And then you find the parameters of this distribution, or estimate the parameters of this distribution, and calculate interval using the estimated parameters. So 3 things: which theoretical distribution statistic follows, calculate parameters of the distribution, and then use the parameters to calculate the interval. Okay, I'll show you how to do it for 3 different statistics, for the proportion, for the average, and for the standard deviation, or for variance in this lecture. But in fact, you can use this approach for any statistic. We are going to learn much more statistics during this course, and most of them have known theoretical distribution. So you can use this approach for many different statistics as well. To give you a better intuition about confidence intervals, I will use several shiny applications in this lecture, and I would like to start with confidence intervals for a proportion. Okay, I think that's the simplest to understand. And that's what you see here. You can also find this application just after this lecture in OpenEDX. The idea is following. This is our population. Okay, we have 400 circles or disks of 2 different colors, blue and red. Okay, this population has one parameter. It's a proportion between red and blue. So if we have 0.5, it's 50-50. If, for example, we have 0.2, you can see that we have fewer red disks, so it means that 20% of the disks are red and 80% of the disks are blue. Okay, so you can change only one. This is the population parameter. It's a proportion. Okay, I will get back to 0.5. Now the idea is following. In this case, we know the population parameter. We assume we know it, and what we would like to investigate, how far statistic of every sample we take will go from the true population parameter. So meaning, if we take a new sample, how far it will go from 0.5? Can it be 0.1 or 0.3 or 0.4? And also how they will be distributed, these statistics. Okay, so let me show you just one example. I will start with sample size 10. You can choose sample size between 3 and 20. We will discuss how sample size influences that. So let's start with 10. Okay, so I click on the button, new, take a new sample. Okay, so that's my sample. Look. So in my sample, you can see the sample objects here with these disks with a little like hole in it. So you see 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so that's the absolutely random sample. Okay, so in my sample, I have 3 red disks and blue and 7 blue. So even though the true population parameter is 0.5, when I took a sample with size 10, I got a wrong statistic, right? So it's not exactly 0.5. My statistic is 0.3, okay? Now you can see here how many samples we've taken so far. Only 1. This is confidence interval based on population parameter. So I calculated it not based on the sample, but based on the population parameter. How? I will discuss it later. I know the formula, and then you will learn it as well, okay? So I know how to calculate it. What it means? It means if it's 95% confidence interval. It means that if I take 100 samples, 100 random samples, 95 of them will have statistic proportion in between. So you can see 0.2, 0.8, quite widespread actually, right? The true is 0.5, but it can go 0.3 below and 0.3 above. 95% cases. 5% will be even more extreme. So it means they will be outside this. We will check if it's true. Now look, this is number of samples with proportion outside these intervals. Our proportion is 0.3. It's exactly in between, so we don't have any that go outside it, okay? The blue curve, it's a theoretical distribution, so it means that every time we take a new sample, the statistic, the proportion for the sample, will be somewhere here, okay? And the orange line shows this confidence interval. You can see 0.2, 0.8. The red dot, it's our sample, so we have 0.3, so that's our sample, okay? This is distribution for our sample. We have only one sample, so we can't say anything about distribution so far. Now let's take a second sample. So now we were lucky enough to get the sample with the same proportion. So again, we have 7 blues and 3 reds. And you can see that the position is different, so it's absolutely random sample. Again, we have 2 samples taken and then the 0 samples outside this interval. So I will take 10 samples. So 3, 4, 5. Let's take this one. Look, now we have only 2 blues and 8 reds. So the proportion is 0.8, but it's still within the interval. You can see it's just on the corner or on the border. Okay. So look, even though the true population parameter is 0.5 and sample size is relatively large, it's 10, we have a big spread of the proportions. We have a big difference, relatively big, of course, difference between the true population parameter and the statistic of a sample. So that's why it's very dangerous to use point estimate, because if you have a sample like this, you will see, oh, the proportion is 0.8. But if someone else takes a new sample, and for example, it will be, I don't know, like this, he said, oh, you are lying, the proportion is 0.4. But both will correct, because the proportion, the true proportion, should be somewhere between 0.2 and 0.8. Okay, if you know the population parameter. So let me repeat it many times, so you can see that it can be, most of the time it's within the interval, okay? So let me do it 30 times. So now I took 31 sample, all of them were within the interval. We have a pretty big spread. Okay, for example, in this case it's 0.2. So only, based on this, we will think that only 20% of the reds. But of course it's not true, because in reality we know it's somewhere between, but where, in reality, we don't know, okay? So I'll just continue. I'll try to take the 100 samples, just try to make it faster. And you can see most of the time it's within the interval. Okay, so it's not that bad. Let's see if we can get at least some outside the interval. Okay, so look, I was lucky enough. I took 100 samples, but none of them are outside the interval. So this is this 95%, it's like an average. Sometimes if it works only if you take like million of samples. Sometimes it will be plus minus. Like it can be 10% and can be 0, like in this case. So let me just continue. Hopefully we will get some outside the interval soon. So you can see the distribution, how it changes. And now you see we got at least 1. So 1% of the samples is this one. It was outside the interval, okay? And then I will just continue a little. And then you can see that the distribution of the proportions is pretty close to the theoretical distribution now, right? So if you take it like 1000 times, the distribution of the proportions will be exactly like a normal distribution, like the one is described by a blue line. Okay, so now you see we have 2% already. It's not the number of samples, it's percent. So we have 266, almost 300. It means that about 6 samples were outside the interval, and you can see them here. Okay. So the first thing is that every time we take a sample, we got a random and calculate statistic. It's random. It varies within certain interval around the true population parameter. But if you don't know population parameter, you can say you can do something. I will show you in a minute. But in general, you will have some uncertainty. So you can't make a point estimate. You can also make an interval estimate. But the good thing is that most of the time, it doesn't go that extreme, okay? So most of the time it is within a certain interval around the true population parameter. So if you know this, how to calculate this interval, you can make an interval estimate for the population parameter, okay? Now let me change the sample size to 20, okay? So 20. Now look, the confidence interval is much smaller. I need to reset statistics first and take a new sample. So that's my new sample, and you see the proportion is 0.6, and the confidence interval is smaller. Now it tells that in 95% cases, your proportion will be between 0.3 and 0.7. Okay, so the larger sample, the closer it approximates the population, and therefore the uncertainty will be smaller. So if you want to be more sure, take larger sample. If you can't do that, well, you will have larger uncertainty, but still do something, still say something about the population. So let me just repeat it several times again. You see, most of the time we still have all proportions around 0.5, so it doesn't go that far. So if I took it, for example, 50 times, let's see if we have at least 1%. No, we don't have any outside yet. Now we have some, okay? So let me do it 100 times. Let's see how many values will be outside. So I did it 100 times, and that's the how many values in percent we got outside the interval. Well, theoretically speaking, it should be 5%, but we got 2. Of course, if we repeat it many times, we will get exactly 5. So that's a matter of big numbers. So that's the intuition for the confidence interval. But in this case, we build this interval based on the knowledge of the population. Okay. In the next video, I'll show you the same, but assuming that we don't know the population. So we know only something about sample.